Bismillahirrahmanirrahim. We shall continue with chapter 4 about population dynamics. Now we should talk about limiting factors. We have previously alluded to some limiting factors in an environment, factors that limit the growth of living things in a certain area. And limiting factors include abiotic and biotic factors. We shall talk about these briefly. Limiting factors, or factors that limit the growth of populations, can be divided into two broad categories. The first is density independent factors, and the second is, of course, the counterpart density dependent factors. The first, density dependent factors, means that how this limiting factor affects the population depends on the density of the population. Let me repeat that again. Density dependent factors are those factors whose effect on the population is dependent on the density of the population. For example, disease. Disease affects populations differently. A disease that affects a population that's dense can be very devastating to that population. A disease that affects a population that is sparse, far apart, may be more contained, because if infectious processes particularly can spread from an individual to an individual. So density dependent factors, an example would be disease, because the effect of disease on the population depends on the density of the population. Another example of a density dependent factor is competition. The more individuals there are, there's greater competition in the population. Also, predators is a density dependent factors. Parasites and food, these are all examples of density dependent factors. Okay. Now, this is an example of a plant that's affected by a disease, and this will spread very quickly because its whole field is the same plant. On the other hand, density independent factors are those factors that are not that cause equal damage. They cause equal damage whether it's a very sparse population or it's a very dense population. So density independent factors, they don't care about whether the population is dense or not. They will cause their equal damage to both, or they will cause equal effect to both. So limiting factors, again, can be divided into density dependent and density independent. Examples of density independent factors are, and these are usually abiotic, you'll see, fires. See, fires will affect a forest, and it doesn't discriminate whether that area is populated or not populated. Volcanic eruptions, floods, droughts, or earthquakes, these all do damage indiscriminately into the environment. So there are factors that are density independent. So density dependent factors and density independent factors. Now, we have spoken of this briefly before. Organism interactions also limit size. Okay, this is competition and predation. Okay, is levels the population off. Previously, we gave the example of the moose and the wolf. I think here is a very similar example of a rabbit and a fox. As the rabbits grow, fox eat them, and the population of rabbits decreases. When the rabbits decrease tremendously, the fox have nothing to eat, so their population decreases. When their population decreases, okay, then there are less predators, so the rabbit population, and the rabbits breed like rabbits, they grow really fast, they climb, and then they go back and forth. So in this way, both predator and prey affect each other, and this is called the predator-prey cycle. Predator-prey cycle, where the peaks and valleys of the predator and prey follow in close succession to each other. So this is important. Organisms' interactions limit the size of the population. Okay, this is another example. Now, here's another point. I just want to use this similar example here. Now, when the rabbit population declines, okay, over here, right, and the fox declines, these are very happy rabbits because they have a lot of natural resources available to them, right? A lot of natural resources available, and not a lot of other rabbits to share with them. So because they're few in number and natural resources are vastly low, their population expands dramatically. See, right? And they get all the way up to here, and then the fox started to decrease. So the growth here is rapid because these guys have less food and less resources to share than over there. So their population typically grows very fast. Okay, this is pretty much. In animals, at least, they have done studies that in crowding of animals, it causes certain physiologic and otherwise stress. In crowded populations, apparently individuals express stress in different ways. When animals are more aggressive, and there's decreased parental care of the animals, there's decreased fertility of the animals, and there's decreased the resistance to disease. Some of this may also apply to humans. So there are substantial negative effects in high density population area for organisms. Okay, so when the population grows, crowding, okay, population density, okay, itself can become a limiting factor. Okay, population density itself can become a limiting factor, and which levels the population off at the carrying capacity. So this is a summary of our discussion here. In the beginning, the population increases slowly, but then the growth is very quickly, exponential growth. There's a rapid growth in the beginning, and then it levels off near the carrying capacity, fluctuations between limiting factors and interactions between other factors. Okay, and that's the typical population growth chart. Now we observe also that there's great biodiversity across the globe. The closer species are towards the equator, the more biodiverse they tend to be. Okay, so this is the most biodiverse species towards the equator, particularly in the rainforest that we have suggested. The farther away you move from the equator, the less biodiverse the ecosystems tend to be. Now we shall shift slightly and talk about human population growth and human population dynamics. It has been, and you probably already know this, human population did not start to grow exponentially until the last few centuries, and it really started growing actually after the 20th century. So human population, at least from the human history, overall had been very stable. And because of basically human mastery of the environment and industrialization, which allows food production and better technology and antibiotics that allows people to live longer, for these various reasons, the human population started to expand exponentially and continues to do so. For example here, from 1800 to 1930, there were about 1 billion people, all of the human history up to that point. From 1800 to 1930, there were 2 billion people. It took only 100 years, or a little 130 years to go from 1 billion to 2 billion. To go from 2 billion to 3 billion, it took 30 years only. And to go from 3 billion to 4 billion, 15 years, and then 12 years and 12 years. So human population is expanding substantially. This word, demography, is the study of human population size, density, human population size, density, and distribution, movement, and its birth and death rate. In other words, what's going on with the human population? Where is it increasing and decreasing, etc.? And this is of great interest because there's disparity between the developing regions and the industrialized countries. Industrialized countries, as you can see over here, they try to politically correct to say industrialized regions, or industrialized countries tend to have a slower population growth compared to developing countries that tend to have faster population growth because they tend to have fewer kids than the third world countries, developing countries. The growth rate of a particular population, so here's a population, see? So the number of individuals in the population really depending on how many new peoples are introduced to the population by birth, okay, or people who migrate or immigrate to that population. So the population size depends on what the population was, plus the new births, plus the people coming into that population or immigrating. And then you have to take away the people who die, or the death rate, and the people who emigrate with an E, who leave the population. Okay, so the population of an area at any given time depends on the population that was there, the birth rate and immigration rate, minus the death rate and minus the emigration rate. Okay, so this is the population growth rate is calculated by these four parameters, as you can see over here. Okay, so immigration of people coming in, emigration, of course, of people who are leaving. Typically, to be a great nuisance to all students, birth rates are given in live births per 1,000 in a population. So the birth rate is given live births per 1,000. And this is why don't they make it 100? Because instead of 1,000, right? There's a reason for that. Thankfully, the birth rate is slow enough that they're making it less than 100 would be not as meaningful numbers. And birth and death rates therefore are given in thousands per thousand, because fortunately, unlike before, where lots of babies used to die at childbirth and lots of mothers used to die at childbirth, live birth rates have improved. So these numbers are small, and that's why they're given per thousand. Nevertheless, birth rate and death rate are given number of live births and number of deaths per 1,000 people in a given year. And as I suggested, population depends on the birth rate, subtract the death rate, and add the immigration rate, and subtract the immigration rate, okay, at any given particular time. There's a concept called doubling time, or the time it takes, the number of years it takes for population to double its size if it were to continue its current growth rate. So doubling time, because those graphs, remember, we're going from 1 billion to 2 billion, 2 billion to 3 billion, 3 billion to 4 billion, 4 billion to like that. So doubling time is of interest to people. See how long will it take for the population of Earth, for example, to double? So doubling time is calculated by life expectancy divided by the growth rate, annual percent. Typical life expectancy, if it is 70, for example, and that's as a big ballpoint number that's taken as an average life expectancy divided by the annual percent growth of a certain area, and this gives you approximately double time, a doubling time of that particular. So this is a formula for doubling time. It can be nuanced if you wanted to give more accurate results. Okay, it's called the rule of 70 because 70 is taken as average lifespan. Okay, it's the 70 divided by annual percentage rate for that particular country. The rate in certain parts of the world actually decreasing, like Japan, so it's not always a positive growth. Now, we're almost to the conclusion of the chapter. This is the last slide. So these are three graphs of three patterns of population change in a particular society. If you go and take a look at a certain country, you will notice, and this is a very remarkable phenomenon, this is perceptible for the first time you step off an airplane if you were to travel to different parts of the country, different parts of the world, and you observe that in certain countries there are lots of young people. Like if you go to Saudi Arabia, for example, or something like that, you'll see a lot of young people. So this is the number of people, and this is age. Okay, so in rapid growth in Kenya, they have a lot of young people and fewer in the middle and less up on the top. This type of graph describes a geographic area where there is rapid growth rate, because these young people will mature and then into reproductive age, and then each of them will have children and contribute to a rapid growth rate. So this is a graph like this of a population suggests that that population is growing. So you can take a sample picture of a population, and if however the demographics are, however this percentage of each age group is, you can kind of tell how fast that population growing. So if you walk to a place and there's a lot of young people, that means that population is growing very rapidly. Compare this, for example, to the United States, where slow growth, okay, where population is reasonably stable and kind of grows slowly. So if you take a snapshot of American population in a certain area, you'll see certain number of kids and is comparable number of grown-ups and fewer older folks, because they tend to die off. So if the population is growing slowly, it tends to, a snapshot of that picture will look something like this. On the other hand, if a country's population is declining, you will see fewer young people and bigger, more adult people, and of course fewer older people. So this sign is a marker of a declining population. So if any country, you walk in there and take a picture of a big city, and you observe these particular patterns, you can just look at the pattern and determine what the population dynamics are of that particular city. If I'm of course simplifying. You can't look at a city necessarily. You have to look at a population, a bigger population. But if there are lots of young people, and then there's a rapid growth, and then the next time you come by, there's going to be many more people going in the area. And if you see a distribution like this, it's a slow growth rate in that country. And if it's like this, where it tapers off at both ends, it suggests there's negative growth. The population is actually declining in that geographic area. So this concludes our chapter. Next time, inshallah, we'll continue with chapter 5. Until then, as-salatu was-salamu ala rasulillah wa ala alihi wa sahbihi. Assalamu alaikum.